All right, recording started here. Happy Wednesday, April 22nd, Earth Day. I, just because I saw this yesterday, um, found this 1 minute video. So you won't hear anything. I mean, in the recording you'll hear the goat babies in pajamas. Come on. So you won't hear any of the audio in this YouTube video unless you find the video yourself later. But look at that! Look at that goat with the strawberry pajamas! Ah, and the prancing, and they're buying, or what is that the noise that goats make? I don't know what. Ah! Ah! And the running. They're so happy. Okay. All right. Ah, there's only 10 more seconds. We'll just. Ah! Okay, that was. All right, no more Aldi commercial here. All right, move that over. That was fun. Okay, move this timer over, and we'll just say, let's see, welcome. Um, Usual comments, right? Like office hours, these usual times. If these times don't work, send me an email. We'll set up an appointment. We'll meet at some other time. WebEx is the preferred method, but look, I realize not that doesn't work for everyone. So call in for an audio link. If we need to, like, if there's some visual things to present, I'm trying to get creative and like, how about share a Google Doc with me and we'll both type in there. Just things to try to be creative in our process to try to make office hours work. I'm trying to think of everything I possibly can as far as solutions. Um, for things like that. Tomorrow there will be an online quiz, so please think about doing that. And then today, I would strongly suggest you start web work number 37 instead of putting things off until the last minute. What I want to do is start by going through the step-by-step process of what this substitution method is doing. First of all, just to summarize, it is undoing the chain rule. And what you need to do to pick U is pick the interior function of the chain rule. Now, I'm going to basically have the same steps in the same order as yesterday. It's just, excuse me, it's possible to now include just slightly more detail than before. So last time was like, this is new. Now I think I can help, based on the examples we had yesterday, clarify a little more, and then we'll do an example in a moment. But step one is pick U equals something, right? So what that something is going to depend on the specific problem you have. So how do you know? This is my kind of go-to hint. It's what I think about all the time. Is if you see the derivative of U kind of elsewhere in the problem somewhere, that's usually a good choice. It doesn't work 100% of the time, but like at least 90% of the time, this is the right method to go about picking U. So you pick something for U, and then you're going to have to, if you see the derivative elsewhere, so you might, I mean, even if you're unsure about what U should be, just write down U is this, and then compute the derivative. Write it as du over dx instead of writing U prime. And then see if you see what you just computed for the derivative somewhere else in the problem. Then solve for dx. So it's summarized here as just solve for dx, but the first step always in solving for dx is you're going to need to multiply by dx on both sides, because if you'll notice in the previous step, dx is in the denominator. So I say solve for dx to try to keep this short, but hidden in there is your first step in that process is you'll multiply both sides of your equation by dx. Then step 4, and here's where the wording is a little different from yesterday. It's replace this with U, and by this blank spot, I mean that's that same U that was up there in step 1. So yeah, replace whatever you're saying that U should be with an actual written U, and then replace the dx with the work from the previous step. And then what you're looking for is cancellations. What you want to have occur is you want all the x's to go away. That is, you want to go from having a problem that had some x's in it to only having u's. Have only u's, no more x's. And if that occurs, your substitution was successful. So step 5, there isn't really any so much action to do as you're doing a spot check to see if everything worked out. If this doesn't happen, if all the x's don't go away, what you might need to do is go back to the top. You might have to go back and pick a different u. sometimes what you actually have to do is it's not about picking the right u. Sometimes you've got some of these problems that don't require this u thingy at all. Some of these problems don't do substitution. You got to go back to the original methods of anti-differentiation that we talked about, say like on Monday or last Thursday. But we'll talk about that when we get there a little more. The point I'm just trying to make right now is this new thing of substitution, which we started yesterday. Sometimes people are like, this is the only method now, and kind of forget about the earlier things. So this is one tool in the toolbox. Don't allow this to be the reason that you throw away all the other tools that we have. Okay, so anyway, the hope is all of the x's go away. You have an integral problem that has only u's in it. When that occurs, if you have this integral that only has u's in it, the next step is to do the integral that has u's in it. Now, I used to use this phrase a lot, do the integral. I will still use the phrase, but a new thing I'm trying this semester is to really try to really clarify what I mean. And you've heard me say it maybe multiple times. But when I say do the integral, I mean like find the antiderivative, right? So find the antiderivative, meaning undo derivative, like underivative, like the derivative of blah is, so you gotta answer this antiderivative question, and when you do that, please don't forget the plus c. And then once you've done that, then as your final step, replace u with blank, and that's that same blank. I mean, this blank is representing the same thing each time. So I didn't want to present it with these blanks yesterday when we were new in the process. It was probably a little extra confusing, but if you look back at how the steps were written before, there's something unclear about it that I think, with the experience of having seen some of these now, I hope this writing in this kind of blank format helps clear up a little bit. Or if at all anything, I'm just trying to say it a little differently. Finally, like I said yesterday, but I want to just absolutely clarify, and we'll see it in an example. Do step 6 and then do step 7. What I mean is do the integral. That is, find the antiderivative before doing step 7, which is the final replacement of u. Do step 6 and then do step 7. I have seen people try to, regarding steps 6 and 7, I've seen the following kinds of errors occur. I've seen people swapping the order. So people will try to do step 7 and then do step 6. I've seen people try to combine steps 6 and 7. I don't think that's a good idea either. So don't combine. Now here's what I've actually seen a lot of in Math 175. I see people go through this process and they're doing step 1 well, and they're doing step 2, and they're doing step by step 1, 2, 3, 4, 5, 6. They do all these things, these step by step things, and all the steps look good. And then all of a sudden, just like in some kind of effort to want to rush through the question, or I'm not quite sure, people will combine step 6 and 7, which I think is not a good idea at all, because in my opinion, step 6 is the hardest step. So like what I've been a little confused by is like people taking like these individual steps and being very methodical about what needs to happen one step at a time, and then take the hardest step and try to combine it with another step. Like, let's just do step 6. Finding an antiderivative is usually the most challenging thing, so just do that, and then once that's done, then do step 7. Then replace the u finally. That step 7 isn't so bad, but it's just not worth combining it. It's not worth combining this easy step 7 with this hard step 6. Just do step 6 on its own. No point in combining. Not a place to be a hero, right? And then finally, don't skip. Sometimes what I have seen is people have, step 5, they've checked, all the x's have gone away, you have a problem with only u's, and then instead of doing any anti-differentiating at all, without finding any antiderivative, they'll just make a replacement and then they say they're done. So don't skip one of the steps 6 or 7 either. All right, so I want to go through as a review of what we did yesterday. There was a problem at the end of class that we didn't go through, but the slides showed it yesterday, and so this problem is very similar in style. So you can go back to yesterday's slides if you want to later to have another problem of this style. One way to do this problem, I should read it out. It's integral of x cubed times the quantity x to the 4th plus 5, close parentheses, raised to the 6th power dx. Now I said integral of, but I could have very well said antiderivative of. Now when I stare at this, I'm like scratching my head going like, what the derivative of what thing would be x cubed times that stuff in parentheses raised to the 6th? It's not something that's coming to me immediately. So this is where I'm thinking Monday's method of just thinking the derivative of what is this and going, I don't know, right? So probably substitution is the right approach. It's not the only approach for this question. I should just point out that one option you have is take this part right there and FOIL that, expand that out 6 times. you can do that, and then only once you've expanded, then you can you'll have kind of a mess already, and then you can distribute the x cubed. So then you'll have a bunch of terms added together, and then you can just anti-differentiate one term at a time. That works technically. It seems like it'll be very painful. It seems like it'll take a long time to do it that way. So it'll work, but just let's not do that. Instead, I'll go for a substitution, and my thought is to use u is equal to x to the fourth plus 5. My reasoning of why I think this is a good idea, a good choice for you, is because, well, let's just compute kind of off to the side here. Du over dx would be 4x to the third, and then the derivative of the plus 5, that derivative is 0, because the derivative of constant is 0. It's generally speaking, you want to take the constant with you, but the reason I want to use this for you is, well, so then u would be right there. And the hint that we saw in the step-by-step instructions a moment ago was, if you see the derivative of u, so here's the derivative of u, if you see that elsewhere in the problem, this is probably a good choice. Now, I don't see the 4, but we'll take care of that. The 4 will, in some sense, kind of pop in front of the integral at some point anyway. But this x cubed part, I see it elsewhere. And by elsewhere, I mean right here. So that's why choosing x to the fourth plus 5 seems promising. So I'm just trying to like point to this example, point to places in this example to try to talk through what I meant by, if you see the derivative of u elsewhere in the problem, this is probably a good choice for you. So you might say, well, why not just x to the fourth alone? Why this plus 5? So often you want your u to include the constant, and the reason that this is better in this case than using just the x to the fourth alone is because the derivative of a constant is 0. Right? So we just computed it, but I have it typed in here that the derivative of u, or rather du over dx, is 4x to the third. And now we need to solve for dx. It's a two-step process, and I kind of just did the 2 steps in one. So multiply both sides by dx, and then divide both sides by 4x to the third. So this is a good place for me to just wait for a moment and see. We're certainly not done with the question, but are we okay with kind of, there's some explanatory stuff up here, sure, but like, are we okay with the choice of u, with the work shown in these last 2 steps here? I just wait for a moment, see if we're doing okay before moving on. Any kind of question of any kind before we move towards the next steps? I've got a good, but I still want to pause. Thanks for the response. It was just, I want to make sure that everybody heard it and the interwebs audio did its thing, and then okay, so let's then take a look. So you'll notice that kind of what I do very often, and I do this in handwritten work too. You'll see, I'll talk about that in a moment, is I tend to recopy the question here. And it's extra writing for sure. But to me, I like to organize things visually for you where you're like, oh yeah, we thought through these ideas, and now it's time to, first of all, I didn't really have enough space up there anyway. So I recopied the question, sorry about that, but part of the reason to do this is to really demonstrate how the equal signs go. So let's just take a look at that, right? So substituting the x to the fourth plus 5 is replaced with u, because that's what we said u should be. There's still this exponent 6 though, right? That still has to be there. Got to still account for that exponent of 6. It wasn't part of what we said u was, so I had to write that exponent of 6. And then the dx was replaced with the fraction, because we said that dx was du over 4x to the third. So made 2 replacements here. X to the fourth plus 5 was replaced, and then dx was replaced. Now take a look at the new version of the problem. There's still x's and u's, but we can cancel. There's an x cubed in the numerator, there's an x cubed in the denominator. We'll cancel those. So with those cancellations, we'll have integral 1/4 u to the 6th du. Now I want to talk about some things here carefully before moving on. First of all, yes, the x cubed canceled up there, And sometimes the accident that people make is they'll move this 4 that's right there into the numerator. But that 4 should not magically move into the, it was in the denominator before, so it should remain in the denominator. That's why I've written a 1/4 here instead of a 4. The du was in the numerator, so I just kind of pushed that off to the side because I personally prefer not having this in the numerator of a fraction, but when something's not written as part of a fraction, it's a numerator type quantity. So I guess what I'm trying to say is I want you to just stare at this line and then the most recent line, and then I want you to see, other than the x cubed on top and bottom, that those canceled, was everything else accounted for, right? So if something was in the numerator before, it better remain in the numerator after, and if something was in the denominator before, it remains in the denominator after. That's the kind of thing I want you to be careful of, because sometimes people write integral 4 u to the 6th du, but it's integral 1/4 instead of 4. And now take a look at this problem. You'll see this integral problem has no more x's in it, right? It's just u's. So that's good, right? There's no more x's, there's just u's in this problem. And it's at this point that we need to do this integral. So that's that. Okay, so step 5 was this check. If I go back to our numbered steps, step 6 is to do the integral. I want to just off to the side here point out the error that people tend to make, though. The error that people very often make is to do step 7, right? To swap steps 6 and 7. So if you do step 7, so that's to make that final replacement. I've seen people do this quite a lot in Math 175. So it's to replace the u with, we have it up here, x to the 4th plus 5. Now, there's nothing, I need to watch my words here. There isn't anything technically incorrect about what's being written, because this is in fact equal to that. However, we're very stuck at this point, right? Because the issue is, look, this problem has x's, and there's a u, so there's 2 different variables here. There's also this symbol, which means antiderivative of. This is kind of a mess, isn't it? Like, there's 2 different variables and antiderivative of. So I don't want to deal with, I mean, that's just, this sounds painful, is what I'm trying to say. So instead of doing that, that's going from step 5, skipping over step 6 and trying to do step 7. You know, maybe somebody's skipping step 6 altogether, or they're trying to combine steps, or they're going to swap step 6 and 7. One of those kinds of things. Like, don't do that. The true benefit of what we have here is that there is only one variable. So let's not move. If you go from step 5 and skip step 6 to do step 7 first, then you create this 2 variable situation, which is no fun. So instead, we'll do step 6, which says to do the integral, to find the antiderivative. So the 1/4 you get to copy because it's constant times function. We have to undifferentiate. We need to antidifferentiate u to the 6th. So think of undoing the power rule. Remember, for the power rule for derivatives, you lower the exponent by 1. So this undoing of the power rule, that this anti-differentiation process or integral process does, it raises the exponent. So the 1/4 is copied. We have u to the 7th over 7 and a plus c. So notice in this step, this is doing the integral. We have a step that has the integral symbol and a du, and the next step no longer has those symbols, it instead has this plus c. Okay, so that's going from this step, going from here, writing that work to writing this work is what step 6 is about. Then step 7 is to finally replace the u. See, step 7 is nice because we don't have to think about antiderivative anymore. So step 7 is to replace the u with x to the 4th plus 5. So that completes the problem. And I'll just make there was a typo I discovered last section, but even though we're done with the problem, I'll just make the point that you can always check your work. So if you take what was here before, and I just kind of copied it down here small other than the typo, and if you differentiate that, differentiating this shown here is going to require the chain rule. And if you do differentiate this, it's going to result in this text right there, box at the top. So it's worth checking on your own. And then I'll just comment a common error that people tend to make out of laziness, carelessness. I'm not sure exactly what term to use. Is writing this dx here absolutely matters. When we were first learning the topic, it didn't seem like this was important. But if you don't write the dx, how are you going to replace dx with a fraction? And that was critical, excuse me, to creating the cancellation that needed to occur. So it's a thing to watch out for. Oh, I should do that. I should just keep that there. These dx's matter. Be sure to write them where they belong. And I will say a sort of the key thing is when you are down to just one variable, that's when you need to think about an antiderivative. So at some point you have to do an antiderivative, and that's true whether you apply substitution or whether you don't. So here's sort of a summary reminder of all of our antiderivative rules. The antiderivative of x to the nth is x to the n plus 1 over n plus 1 plus a c, as long as the exponent isn't a negative 1. In fact, we just applied this property in the question we looked at. If the exponent is a negative 1, then the antiderivative is ln of absolute value of x plus c. If instead the fixed thing isn't the exponent, but the fixed thing is the base, so you're anti-differentiating b to the x, then the antiderivative is b to the x over ln of b plus c. Constants, a constant times a function that you're anti-differentiating, the constant can come in front, just like with differentiation. The same is true for anti-differentiation. So constant times then the function you need to anti-differentiate. Sums and differences work out super nicely, just like for derivatives. Products don't. Right? So if you had a multiplication sign here, you can't just split this up. There's no product rule in that format for integrals. So if you see a product, you probably have to do something like distribute or FOIL or something like that first. Same with a fraction. There's no quotient rule for integrals. You'll instead usually have to manipulate the fraction using some algebra first. So anyway, these are just as a reminder or review, the anti-differentiation rules that we had before the chain rule. And what I'd like to have you, oh yeah, and then just this comment down here as a reminder that if you see that dx in the numerator, I know it looks a little annoying like that. You can always just push it off to the side, right? And then at least written like this, it looks a little more normal. Integral of 1 over x dx. This 1 over x part, you can, of course, rewrite as x to the negative 1. That's an algebra step, which is why this integral sign is still written. And then this integral of x to the negative 1 dx, that's up here I copied, and that's ln of absolute value of x plus c. So yeah, this slide includes a lot of kind of review of these old formulas, but these things apply at some point because, in like step 6 of the U substitution process, you need to find an antiderivative. What I have for you then is I'd like to ask you to work on these. All of these questions should be done using this new U substitution method. I'm going to stick around here. You don't have to go in order if you don't want. I will say that they do get a little more challenging towards the end. But yeah, 1, 2, 3, 4, 5, 6, 7, 8. You can, at any point, unmute and say, I want help with this, or I want a hint, or you can type and say, I want a hint, or can we work out this problem completely, or whatever. So I want to just give you most of the class time. I just have like a 5-minute wrap up at the end to practice these. But I'll walk around the room, as it were. How are we all doing so far? Are anybody have requests on, I would like a hint on this problem or anything like that? Oops, I thought I was typing privately, but that's why I include a 4 question 3. Cool. And I mean, the reason it works, right, is that the derivative of that is 1 minus e to the x, and I see that elsewhere in the problem, namely in the numerator of the fraction. Is there any problem that anybody wants to see like fully worked out? I mean, I have like the kind of thingy up here where I can write on screen if you'd like or not. I mean, everybody's so silent. You just kind of want to work on the problems you're on your own, huh? That's fine too. Could we go over number 8? Is that, yeah, let's do that. Right. So that was sort of, I mean, it's kind of looks strange. And so that was the one that was asked about last section as well. So that will help kind of create some of the similar experiences. Um, yeah, let's do that. Let's look at integral 5e to the power 1 over x all over an x squared dx, right? As a whole group. So let me go back to this app. And okay, so if I try to do this, it was integral fraction 5e to the 1 over x all over x squared dx. So my thought actually for this one is to use u is equal to 1 over x. Now, I don't want to differentiate this u quite as written. I mean, we do need to differentiate it, but before differentiating, I don't want to use the quotient rule. So I'm just going to rewrite this first as u equals x to the negative 1. Right? So then when you find the derivative, we completely avoid the quotient rule. We just get to use the power rule, negative 1 x to the negative 2, and another way to write that is negative 1 over x to the positive 2. We're about to do things to both sides, but now all of a sudden we have 3 sides. So actually what I'm going to do is just right underneath, skip writing the middle thing, and just have du over dx equals negative 1 over x squared. And as usual, the case to solve for dx, because take a look, dx is in the denominator, we always have the step of multiplying by dx on both sides. So when you do that, you'll have du is equal to negative 1 times a dx over x squared. Yeah, so that's multiplying by dx on both sides. And then, well, we're trying to solve for dx, so there's this x squared in the denominator. How about we multiply by x squared on both sides? So x squared du is equal to negative dx. Now we're so close to solving for dx, but there's still that minus, there's a times negative 1. And the student's usual approach to getting rid of that times negative 1 works. It's to divide both sides by negative 1. While that technically works, it's actually much easier. Instead of dividing both sides by negative 1, just multiply both sides by negative 1. Because if you that way you just have fewer fractions. So if you multiply by negative 1 on both sides, you'll have negative x squared dx, and then negative, so the negative that's already originally there on the right side times the negative 1 that you're multiplying by. Negative times negative is positive. So that's solving for dx. Then we can go back to the question, integral 5e to the 1 over x all over x squared dx, and let's make some replacements. So we have integral sign 5e to the, so this 1 over x that's right there that I just circled, we can replace that with, we have it here, that should be what u is all over x squared. I'll just write x squared for now. And then the dx gets replaced with negative x squared dx. Now, as written, this looks confusing. This looks almost deceptive. So I don't mean the fraction then subtract x squared. I mean the fraction multiplied by a negative x squared. So to clarify that we're talking multiplication, you're going to have some parentheses, otherwise this is ambiguous. Okay, well then the x squared in the numerator and denominator cancel out, and so we're left with integral, you know what, that minus sign, again, I just don't want it to cause confusion, so I'll write it kind of near the beginning. So integral sign, negative 5 e to the u. Oh, sorry. No. Sorry about this. Back here, this should have been a u. I don't know why I had an x here accidentally. This should have been just if I copied the u that was right there. So this should have been a u. I was like, what's going on? Okay, so let's just step back. So we cancel I'll do this in a new color, cancel the x squareds. So then we should have, I'll just write the minus sign near the beginning. integral sign, minus sign, 5 e to the u du. Okay, that looks better. I was just like, what? This mix of x's and u's. So canceling the x squared on top and bottom, and then just juggling the order, writing the minus sign kind of near the front, we have integral negative 5 times e to the u du. If you prefer, you can even bring the negative 5, that number in front of the integral. So you have negative 5 integral e to the u du. And now, copying the negative 5, we need to antidifferentiate e to the u. Well, since e to the u is its own derivative, e to the u is its own antiderivative. So we'll have e to the u, although with a plus c. And then, so that's the step where we do that antiderivative, right? So now that the antiderivative is done, our final step, not to combine things, right? But so we did the antiderivative step. Now we need to replace the u, and I already forget. What was u? It was, oh yeah, up there, 1 over x. Sorry for the scrolling. 1 over x plus c. So there. I can't quite fit it all in one screen, but that should be all the work for question 8. Cool. I would like to do the following. So I will just point out in the slides, I don't have it fully worked out. What I have in the slides, if you just, I'm going to advance it forward real quick, just in case you don't want to see it right now, but it's just u equals, try this. So I'm going to advance past that slide. But then what? Well, I still wanted you to see solutions. And so I thought I had some handwritten solutions. I couldn't find them. So yesterday afternoon, I typed up a full set of solutions. So let me show you where you can find them. If you go to the home page, I think it's called, for our Canvas course, you'll find it in this list. Just kind of scroll down a little bit in this learning resources kind of handouts, things I'd normally print out and give to you. There's a copy right there called Substitution Example Problems from April 22nd Solutions. The other place, you'll find it in modules. It's the same listing of things. So let me just click on that so you can see it. What I have here is if it would load, come on. Okay. It's shy today, right? So what you'll see that I did is I actually just, based on the slides, you see it's all the same font. I screenshotted just one portion of a question, and then I hand wrote an answer. Now, I think the benefit of a handwritten answer like this, as opposed to me typing, because it takes about just as much work either way, whether I hand write a thing like this or type. But I think the benefit of seeing kind of clean handwritten work is that's probably what you're doing with most of these problems. Like I get that in web work, you're going to type the final thing in, but just to see how the work looks organized, I think that's helpful to see in this format. So I hope this is helpful. I hope that you will go through this. Your steps might not look identical to what I have here, but when I have an integral sign and you don't, I want you to sort through, wait, should I have an integral sign or not? Did I make a mistake? That's also possible. These are some of the things I want you to be thinking about. I just, actually, in the last 6 minutes here, I just want to wrap up with these ideas then. I just want to say what's going on when you do the substitution thing is do that integral that has a u. What I mean is, find an antiderivative. That's what I mean by this phrase, do the integral. After doing that, then you substitute u, and sort of the other way, kind of back the other direction, right? Sometimes you do the integral, that is, by do the integral, find an antiderivative. You sometimes do this without doing any substitution of any kind. So this substitution technique it's new as of yesterday for us. And so Monday we did some integrals. We found antiderivatives without any substitution of any kind at all. And I just need to point out, like, if you think every problem will be done using substitution, it'll get you into some trouble. Sometimes what you'll need to do is to do the integral or to find the antiderivative, you need to just do some algebra. You might need to take a product that's written in, FOIL it out, expand it. That might be the step you have to do. And then you might need to do substitution, or you might again not, and you might just need to antidifferentiate each term one at a time. So, and then here I keep using the phrase do the integral. What I mean by that is find the antiderivative. In fact, just to speak about that process a little bit, what I mean by do the integral is, so when you see that symbol, please think internally to yourself, say internally, antiderivative of. Like that will help you sort out when you need to write it or not. So what does doing the antiderivative look like? So one step has this integral sign and then either a dx or a du. So if you were doing substitution, I guess you'll have a du. And then the step after, so in the process of doing the integral, the next step that you write down won't have either of those features. Instead, you'll have a plus c. So if I go back to even the work that we just wrote in, we had this step, and then that step. And so the thought process of going from there to there is doing the integral. It's going from having the integral notation to no longer having that and having a plus c instead. So when does that switch occur? It's when you're stating the antiderivative, when you're thinking about what the antiderivative is. And again, you've already heard me say it, but I just want to like really clarify that this new method, substitution, it doesn't always apply. It sometimes applies. And so tomorrow we're going to dig into that issue a little more with kind of varied practice problems. Some practice problems are the kinds that I could have given you on Monday or last Thursday, and they'll be kind of mixed in. Just for the round of announcements again, online quiz tomorrow. I strongly suggest starting web work number 37 today. And finally, just so you can see the preview of it, tomorrow there is a warm-up, or rather two-part warm-up. One of the questions, I'll just hint now, requires substitution, and one of them doesn't. So see you tomorrow. We'll end 3 minutes early here.